In this section, we dive into our next operations, which are multiplying and dividing involving radicals. So really, we're just going to jump into doing a ton of examples because we've really been working with this concept nonstop. The only difference is now it involves a radical. So we're going to start by just multiplying some expressions. And in the same way we've dealt with this before, anytime we're taking one expression and timesing it by another, we're basically applying a distributing process. So we're going to take this square root of 6 and we're going to distribute it to both pieces. So we're going to have 3 times the square root of 6, and then we're going to have the square root of 6 times the square root of 2. Okay. Now for this first piece, there's nothing I can do to simplify that. But for the second one, because we have the same radical, we can go ahead and multiply what's underneath. So this is 3 square root of 6. And then when we combine that to a single radical, it would be 6 times 2. At this point, you probably can start skipping a couple steps. We just get the square root of 12 underneath. Now remember, we always want to simplify these expressions as much as possible. And unfortunately, the square root of 12 isn't fully simplified. So what we can do is we can write 12 as 4 times 3. So this way that 4 is a perfect square and it will pop out. So this becomes 3 square root of 6 plus 2 square root of 3. And then from this point, there's nothing I can do to simplify 6. It's not divisible by a perfect square, and neither is 3. It's a prime number. So that's as far as we can possibly go. Okay. For this next one, we have a bit of a different process because it's not a single term times a single term. We really have exactly this binomial that we've been working with. So in the same process, we're just going to FOIL this expression to actually multiply it out. So if we multiply the first terms, we'll have square root of 2 times the square root of 3. Then our outer terms going to be negative 1 times the square root of 2. So I'm just going to write that as minus root 2. If you need that 1 out front, absolutely feel free to put that. The inner terms are positive 1 and square root of 3. And then the last term is positive 1 times negative 1. So we get a negative 1. Okay. And same thing again, we now just need to simplify. So for the first two, we have a radical times a radical. We can multiply underneath. Then we have minus square root of 2 plus square root of 3 minus 1. And at this point, all of these radicals are as simplified as possible. Again, 6 is not divisible by a perfect square. 2 and 3 are prime, so we can't simplify this anymore. So let's try one more. Now we're going to take kind of a unique expression, and so this will come back into play a little bit later. We have a binomial times a binomial, and they're almost identical. The only difference is the signs are opposite of each other. So let's see if something nice ends up happening here. So if we go ahead and FOIL this out, the first terms would be square root of 7 times the square root of 7. The outer is positive 2 times the square root of 7. The inner is negative 2 times the square root of 7. And then the last is minus 2 times positive 2. Gives us a minus 4. So if you notice, the outer and inner terms happen to be exactly the same thing, but opposite in sign, so those cancel each other out. So what we end up with is square root of 7 times square root of 7. We can combine that under a single radical. So 7 times 7 is 49. And then we have minus 4. But square root of 49 is a perfect square. It is 7. So we really are just doing 7 minus 4, and this ends up simplifying to 3. So this is a really nice process when you take a binomial and you times it by almost itself. It's going to clean up really nicely. So this is a process that's called multiplying by the conjugate, which again we'll see in a little bit. Now let's go ahead and get more practice with rationalizing. Remember, we had already talked about this, so we don't like having square roots in our denominators. So the way we can rationalize is by going ahead and multiplying by what we see, or trying to get rid of that denominator. Okay, so we'll see an example where we don't multiply by exactly what we see. So for this one, to get rid of a square root, remember we can just multiply it by itself, because we would combine under a single radical, and that would give us a square root of 36, which just simplifies to 6. But what I do to 1, I have to do to the top. So really, we end up with 5 root 6 divided by 6, because those square roots cancel. For this next one, same thing. We need to multiply by square root of 7 in the bottom to make it cancel. And so what that gives us is 7 root 7 divided by 7. But now we can actually simplify this even more. The 7's cancel each other out. And all of this to get that it is equal to the square root of 7. For this next one, same thing. I'm going to go ahead and just rationalize first. So we go ahead and multiply by the square root of 48. And so we get 7 root 48 over 48. Now the square root of 48 actually can be simplified a bit. So it is divisible by 4, but it actually can be divided even more. If you divide it by 16, you will see that it is divisible by that. So 48 can be written as 16 times 3. And then we can take the square root of each of these individually, so we get a 4 that pops out. So we're left with 7 times 4, square root of 3, divided by 48. Okay. Now 7 over 48 doesn't simplify, but if I take 4 and divide it by 48, it will simplify. So 48 divided by 4 ends up leaving us with a 12 in the bottom. So this simplifies to 7 root 3 divided by 12. Okay. Now for this next one, I don't have a number inside that square root, but I'm still going to apply exactly the same process. To get rid of a square root, we multiply it by itself. So we're going to take top and bottom and times it by the square root of x. So we're left with y cubed root x in the top. And then those radicals cancel each other out, and we're left with just x in the bottom. Now let's try one more of these, but it's going to be very different than anything we've done before, because we're trying to rationalize something that has a cube root. Okay? So cube root times a cube root, we're going to see doesn't actually cancel each other out. So what I'm going to do is I'm going to go ahead and try to apply the same process and take top and bottom and times it by the cube root of x. So in our numerator, we're going to be having the cube root of 2y times the cube root of x. And in the bottom, because you're taking this expression and timesing it by itself, what you can think of that we have is we have this thing to the second power. And unfortunately, at this point, the cube and that second, or the cube root and that second power don't cancel each other out. What I would need is something to the third power. So what I really have to do at this point is I have to multiply it by another cube root of x in the bottom. And so I'm going to show you a different way after this that might make it a little bit easier, but we have to take a slightly different approach for roots other than our square root. So what we end up getting now is we have the cube root of 2y times the cube root of x times another cube root of x. And in the bottom, you can think of this as to the first power. They have exactly the same thing on the inside. So we really have the cube root of x to the third. Okay. And now at this point, we can go ahead and say that cube root and that cube cancel each other out, and we just have an x in the bottom. And then in our numerator, because they are all the same radical, we can go ahead and just combine what's underneath. And we have 2y times x times x. So the absolute simplified that we can make this is 2y x squared under that cube root, and then overall divided by x. So it definitely takes a little bit more for these other radicals. Instead, what I want to do is I really want to try the same problem again, but I'm going to turn this into an exponent. So this way we can see what we need to multiply by to get rid of that exponent in the bottom. So let's go ahead and clear this entire page, and we're going to try it again. So what we're going to do is this top one you can leave in radical form, but in the bottom, let's write that as x to the 1/3. To get rid of this exponent, I would need a 1 here. So what I actually need to multiply by is x to the 2/3 in the bottom, because then we would add the exponents together. 1/3 plus 2/3 is 1, and it will go ahead and wipe it. But again, what we do in the denominator, we have to do in the numerator. So what this gives us is the cube root of 2y times x to the 2/3. And then in the bottom, we go ahead and we add those exponents together. So ultimately, in the bottom, we end up with x to the 1st power. And then we've already worked with expressions like this. We know how to rewrite them. So this is the cube root of 2y, and that third being in the denominator tells us we're taking the cube root of x squared. And then from here, we can combine it to exactly the same expression that we found before. So either way ends up working. It's a personal preference for you. So now the very last thing we're going to do, if we have division involving radicals, getting rid of that denominator can be tricky if we have a binomial. So that's something that has 2 terms in the bottom. So basically we'll see something of the form a plus the square root of b, a minus the square root of b, something like that. But in order to get rid of that expression, we're going to multiply by what's known as the conjugate. So if you have a radical expression involving 2 terms, the way we can clean this up nicely is by multiplying by the same expression, except we're going to change the sign in front of that radical. Really, you could also change the sign in front of the constant. So if I go way back up here, when we multiply these 2 together, they really are conjugates of each other. They simplified really nicely to just 3. So anytime we multiply a number of this form by its conjugate, it will clean up great. So all we're going to do is we're going to try a couple examples where we need to rationalize this expression. So we've got a number and we're dividing it by this binomial. So what I want to do is I want to take this expression and I want to multiply by the conjugate. And really the easiest thing is to just change the sign on the radical. It's less likely for you to forget. Okay. So what we have to do is in the numerator, we're going to have 3 times 4 minus square root of 5. And then in the bottom, I have this expression that's going to require us foiling it out. If you want to do the denominator off to the side, absolutely feel free. But now from here, we can go ahead and we'll distribute this 3 to both pieces. So that gives us 3 times 4, which is 12, minus 3 square root of 5. And now in the bottom, we go ahead and FOIL. So our first terms give us 16. The outer give us minus 4 square root of 5. The inner is plus 4 square root of 5. And then the last is minus square root of 5 times the square root of 5. So ultimately, these two middle terms cancel each other out because they're the same but opposite in sign. So in the numerator, we're left with 12 minus 3 root 5. In the denominator, we're left with 16. And then when we take square root of 5 and times it by itself, it just simplifies to 5. So we're able to wipe the radicals completely in the bottom, and we end up with just a constant. So this becomes 12 minus 3 root 5 over 11. Okay. So let's do one more. And now we're going to have a radical in the numerator as well. And we have this binomial in the bottom. So again, I want to multiply by the conjugate of what we have in the denominator. So we keep the numbers exactly the same, but we change the sign on that radical. And then what we do in the denominator, we've got to do in the numerator. Okay. So ultimately, we have a gigantic fraction. We're taking the square root of 8 and timesing it by 3 plus root 5. And then in the denominator, we're going to have to FOIL these two expressions together. Okay. So in the numerator, we end up with 3 times the square root of 8, and then the square root of 8 times the square root of 5. In the bottom, when we FOIL, our first terms give us 9. The outer gives us positive 3 root 5. The inner gives us negative 3 root 5. So they are always going to cancel each other. And then the last becomes minus square root of 5 times the square root of 5. Okay. So in the top, I do have some simplification that I'm going to be able to do with the square root of 8, but I'm going to take care of everything at once. When we multiply the 8 and 5 together, we're going to get 40 under the radical. And then in the bottom, our 3 root 5s cancel. We're left with 9. And then the root 5 times root 5 also cancels. And we're left with a 5. So we're at a point now that we can go ahead and simplify the expressions in the numerator. 8 can be written as 4 times 2. And 40 is 4 times 10. And then in the bottom, we have 4. So in both of these radicals, a 2 is going to pop out. So we get 2 root 2, and then 2 root 10. And then we have a 4 in the bottom. And we're still not fully simplified because all of these expressions have a 2 in common. So you can do this really however you want. You can divide every single term you see by 2, or recognize that you could factor it out, and then you'll be left with a 2 in the bottom. But I'm going to go ahead and factor the 2 out so you can see that what's left over is 3 root 2 plus root 10 divided by 4, and then 2 divided by 4 simplifies to 2. So the furthest we can simplify this is 3 root 2 plus root 10, all divided by 2.